So it makes sense that P plus Q equals 1. Could you close the door, whoever's closest to the door? That P plus Q equals 1. Because if there's only two alleles, then the frequency of one allele plus the frequency of the other allele has to be all your alleles, right? I mean, it seems simple, but it's the simple ideas that can be the most powerful. The other equation that Hardy-Wienberg came up with is P squared plus 2PQ plus Q squared also must equal 1. Let's take a deeper look at what this means. How is it you get this, by the way, is homozygous dominant. This is homozygous recessive. And this is the heterozygote. All right, so again, intuitively this makes sense. If the frequency of the homozygous dominant plus the frequency of the heterozygous plus the frequency of the heterozygous recessive should equal 100% or 1. I mean, again, what other choices do you have? So that makes sense. So why is it P squared? Well, let's think about it. You have two genes from each parent. One of those genes is going to be given to its offspring. These parents' offspring is going to give one gene each. So how do we figure out the odds that one parent is going to give a dominant gene and the other parent's going to give a dominant gene? What do we do to figure out the odds of getting one big whatever and one big whatever? Multiply is correct. I'm just going to use P just to keep the... I need you to understand, though, before I go on, that the P is the frequency of the allele, dominant allele in the population. But I'm going to use P here just to emphasize as the dominant. So it would be P times P, correct? Do you agree? Because they're and. Isn't that the same thing as P squared? Okay. So that's how we get P squared. Because to get a homozygous dominant, those are the odds of getting one parent to give you a dominant and another parent to give you dominant. Does that make sense? And that's going to be the same thing for the recessive and recessive. That would be Q times Q, and that would be Q squared. Again, this is about populations, though, not about individual matings. So I just want to make sure emphasize that. All right, so now that seems simple enough, but then why is it we get 2PQ? Because what are the different ways you can get PQ? How do you get two different ways to get a heterozygous? So let's look at it. There's two ways to get a heterozygous. The first way is if mom gives the dominant and dad gives the recessive. Or what? What's another way? If mom gives a dominant and dad gives the recessive, or the opposite, right? So there's two ways to get it. And we're not using and, we're using what word? Or. So what do? Are we multiplying, dividing, taking the square root of? What are we doing? Adding. We're adding them. So it would be PQ plus PQ for the heterozygous, right? Because there's two ways of getting it. Oh, isn't another way to write this 2PQ? Are they not equivalent? Are these two not the same, different ways of writing the same concept? Yes or no? Yeah. So they're the same. So that's where we get 2PQ. Is that making sense to you? All right. Now I'm going to apply it. Can I go on to applying? All right. So if I tell you that the recessive frequency, let me give you a real example. I have to think. Okay, I'm just going to use white flowers. So I tell you, white flowers are recessive. The white color is recessive. And red is not recessive, is dominant. And I tell you that 20% of the population is white. So what population is red? 80%. That's easy, right? Isn't that easy? Everybody got that? All right. Well, right now, I've said this before, and I said this during when we did pedigrees. I'm going to tell you again. I'm telling you now during this. It is amazingly important for you to identify the recessive. The recessive is your key to a lot of genetic problems. If you have dominant recessive, then recessive is your blessing. So because it's recessive, you know that this is Q squared. You just found Q squared. That's equal to 20%. That's easy. Now, why is the dominant so hard? Because that 80% is P squared plus 2PQ. It's the heterozygote and the homozygote dominant. All right? So it's the two together. You can't tell the difference, right? If I look at a red flower, how do I know it's dominant, it's homozygous dominant or heterozygous? I don't. Well, luckily I have math. Math is a beautiful thing. Because I had two formulas that I know. I know P plus Q equals 1, and I know P squared plus 2PQ plus Q squared equals 1. Those are going to be my salvation right there. Well, I have 20% or 0.2 equals Q squared. How do I find Q? Square root. What's the square root of 0.2? You do the math. I don't have a calculator on me. The square root of 0.2.
About 0.447.
0.447. Now that how does that help me? Well, if I take P plus Q equals 1 and I say P plus 0.447 equals 1, what is P? What's P? How do I find P? Subtract. So go ahead and 1 minus 0.447 is what? I'm sorry, could you close that door? Huh?
0.553.
0.553. So now what I like to do, I'm going to tell you right now, you see how these numbers are all over the page? When you're on the test, it could be just that confusing. You're in college, look, on the AP exam, in college, in physics, in biology, in chemistry, I don't care what it is, you got a page full of calculations. The best thing you can do for yourself is highlight key terms, key equivalencies. So P is that. I know Q is this over here. I got P and Q. I know Q squared. I knew Q squared is here, is 0.2. So I got 3 equivalencies so far. So I got P, but that still doesn't tell me my homozygous. So I know my Q squared, which is my homozygous recessive. I was given that. And that equals 0.2. I need to know my homozygous dominant, which equals, I don't know, and I need my heterozygous. Heterozygous is easy now because I got P and Q. That's 2PQ. That's 2 times P, which is 0.553 times what? 0 what? 0.447. Someone do the math, please. What is 2 times 0.553 times 0.447? 0.49. I'm just going to round up. So that means it's going to have rounding error at the end. Just remember that. But I'm going to go ahead and accept that. So 0.49. Homozygous dominant is P squared. What's that would mean 0.553 squared. What is that?
Zero point 306.
0.306. So I'm just going to put 0.31. So if I add these together, remember 2p squared plus q squared plus 2pq should equal what? 1. So what's 0.2 plus 0.31 plus 0.49? Is it 1? Oh, so it worked out. So it's 1. That's what we expected. We expect them to come out as 1. If the population is at equilibrium. Nolinex, when do we expect this to be at 1? When do we expect all 3 of these to equal 1? Yeah, but I wanted her to answer because she wasn't paying attention. But that's fine. It's when it's at equilibrium. So if that means, what does equilibrium mean? That means when the population is not evolving. When it's not evolving. In real life, it's never the case. In the long run. All right, are we good with this?
So is this all like theoretical?
this is the predicted value. So this is what you would expect to see if there's no evolution.
Okay.
And that's just based on the Punnett square and looking at calculations and saying, look, if I got this many out there, this is what I expect to see. And the numbers actually do work out to be this. So it is theoretical, it is applicable if there's no evolution in the population. But it's a good question. It's like, I always wonder, like, how do you get too picky? What? But these amazing men that we just saw came up with this stuff. They were men. I'm not being misogynistic. All right, can I go on? Yeah.
We have to find the homozygous recessive first, right? Before we can find.
It's a really good question. It depends on anything they give you. So if they gave you the homozygous dominant, then they would give you p squared, then you'd work from that. If they gave you the heterozygote, that would be harder.
I'll say in this case, they gave us the recessive and the dominant, so we just picked which one to decide to go.
They gave you the recessive and then you work from there. They'll give you one of the three, and then you gotta work it out from there.
Okay.
She has a visitor here.
Okay, and I have a visitor. So, that's a good question.